没问题吧？Andy, everything
问题
okay?
Yeah, it's fine. I just start recording.
Yeah, okay, fine. Why do we have need a DC? Okay, it's showing a DC in series with the AC voltage and the current detection. And this DC actually is a slow ramp usually because you want to sweep the gate bias from accumulation to depletion to inversion. And so this is actually not DC. I mean, for fixed bias, the BG is fixed, and then you measure the AC response to get the capacitance. But for the sweep, gate voltage so DC is represent the gate voltage VG here. So in the CV meter, it sweeps VG from 0 to, in this case, 3.5 volt, let's say, in maybe a minute or two, so that it's a slow sweep. And as far as the charge response is concerned, it's essentially a DC for any given bias point. Yeah. So that's this question. Next is, okay. If you bias here, let's say for curve B, you bias beyond the two side B condition, and then the capacitance, the emerging charge cannot respond to the AC modulation, so the capacitance remains due to the depletion. Let me see, yeah, here. So if the immersion layer is formed statically, but does not respond to AC. So the only response for AC is depletion charge, which means that the capacitance is equivalent for silicon capacitance equivalent to the distance of WDM into silicon at the end of the depletion region. Okay, but now that's for capacitance. But now, there's really no change. There is actually some change due to the emerging charge, but not the magnitude. In other words, for a fixed bias, when the AC goes up and down, positive and negative, the emerging charge will respond in such a way that the distribution will be different. For example, when the gate is in the positive cycle, then the emerging charge will be closer to the oxide versus the other side. But the magnitude of emerging charge doesn't change. In other words, the total charge, emerging charge, doesn't change with time at the AC signal, but the distribution may change. Okay, so that's the answer to that. There's actually a reference for that, but we don't bother to discuss it here. Okay, next two questions. It's about if there's a positive charge, fixed charge in the oxide, in the gate oxide, then how does that change? And this actually, in chapter 4, we don't discuss that because for logic application, we try to minimize the charge in oxide, so it essentially has no effect. But in chapter 12, which is actually a memory device, especially the non-volatile RAM or the flash device, we intentionally put put the charge in the oxide. Then it will shift the CV. This shows a positive. This is a positive charge in the oxide, so VG shifts negatively. But the CV shifts negatively. Yeah. So we'll talk about more details later. And also the next question is okay, that was for an energy band diagram. Again, that's in chapter 12. So in chapter 4, we said that we assume that this charge is negligible in oxide. So we draw a straight line because the oxide, if there's no charge, then the electric field in oxide is constant. So the constant slope. But if there's a charge, then there will cause a change in electric field in oxide if there's a delta Q charge here. Okay. So again, this is what we covered in detail. Another thing is 孙院长在不在？Jack, do you wanna
Yeah.
say a few
Let
words?
me. Yeah. Yeah. I can add some comments. 那个
please.
Yeah. Question number 3，像那个 alkaline 这个，它基本上过去从70年前啊，60、70年它是一个那个 mobile ion 啊，所以其实你有那个 sodium 过去在那个 MOS device 里面是绝对不能有啊。那因为有的时候它不光是刚刚陶老师讲的，就是说你假设有正电荷，而且正电荷越靠近那个 immersion layer 或越靠近那个 channel 啊，那边它对那个 channel 的影响就大了。反正正电荷就会造成 VT 就会变小，也就是说，我不需要加那么高的那个 gate bias 就可以 induce 那个 inversion 或者可以 deplete 那个 depletion layer 的那个 purity。所以这个部分是蛮实用的，就是说，但是在 modern MOS technology process usually is very clean. So we don't worry that much. We worry more about some of the radiation damage and other things, which can cause some additional trap states. During process, you could have UV, you could have UV or whatever, and some of these fixed charge or interface states. Those are atomically, you can say, if we don't introduce any foreign atoms, you just break the covalent bonds, okay, and then we can trap charges. Okay, so that's and also for the question, the previous question, in terms of the immersion versus depletion layer small signal. MOS capacitor and MOS FET are very different. MOSFET, you don't have any supply of carriers, right, except from generation. So generation usually is slow, especially at room temperature or unless you have very dirty substrate, have a lot of generation centers. If you are in a MOSFET, 就是 FET 的话，那 source 只要你那个 you bias above threshold 的话，那你那个 carrier 就很容易发了因为它基本上就从 source 那边就进来了。那跟那个后面的那些空乏区的 depletion layer 那边根本就是脱钩了大致上可以不说的比较来看。所以那个 CV 这边有这个所谓的这个往上翘的开始往上跑，那就像 quasi-static 或 static 那种 CV， total capacitance， 那有所谓的一般的 MOSFET 的那个 depletion region， 那个就是基本上immersion layer 是那个来不及反应small signal， 尤其高频那低频的话就最上面右边最上面的颗。那如果说冲得更快的话，那基本上会 go into deep depletion 就是最下面那条颗照不上。那个陶老师，请继续。
Okay. All right, so we go on. Next question 8. How does depletion approximation help in determining the maximum depletion width? Well, we covered this in the MOS case. We assume that the charge change abruptly at the depletion boundary. So outside the WD is charge neutral. And inside WD, all the mobile charge, in this case, Na, that's P, the holes are depleted, so that it shows actually this should be negative ionized acceptors. And so from that, we can integrate the field, and then we integrate again, we get the potential. So we solved the just like a PN junction, depletion width given by the square root of this ratio. In PN junction, the psi S is psi bi plus the reverse bias voltage. In MOS, it's just the surface potential. So when there's a strong immersion condition is psi S equal to 2 psi B. Okay, and so when the psi S equal to 2 psi B, which equal to this, then the depletion width reaches the maximum because now you have a lot of immersion charge at the interface. So that respond to the gate, the more positive gate voltage. Okay? And so in this case, we put this 2 psi B into the depletion width expression. Okay, this expression with psi S equal to 2 psi B. Okay, where psi B is KT over Q log Na over Ni, so you get this expression. So and so this is all derived, assuming depletion approximation, which is valid up to the inversion. Now, once you go beyond the inversion, it's no longer valid because now you have an inversion charge. But at the boundary, the inversion charge is still small, so you can still apply that. Okay, next. Okay, so now the next few questions are PN junctions. High injection. This chart covered the high injection case, and the key is charge neutrality requires whatever the charge change of positive and negative must be the same. And for low injection, which means that the injection, well, first of all, in this bracket, MP0 is always negligible. That's just Ni squared over Na, so that's negligible. So so if delta PP or delta MP is much smaller than PP, which is the majority carrier density, or Na, then the delta MP equal to Ni squared over Na, which is PP, and the e to the QV over KT. Okay? But high injection, the condition is that delta MP is much larger than PP. In that case, the first bracket is no longer dominated by delta PP. I mean, no longer dominated by PP. Instead, will be dominated by delta PP, which equals delta MP. So the left side becomes delta PP or delta MP squared. So now you solve by taking the square root on both sides. So now we have delta MP equal to Ni e to the QV over 2 KT. So that's the key difference is that low injection is the minority carrier injection on the other side is e to the QV over KT. High injection is e to the QV over 2 KT, and this can be observed in the IV curves as function of V applied. Okay. Next question. Sigmoid doping difference. Okay. when we cover the depletion approximation, okay, we assume the NA and ND, arbitrary NA and D, except that it's got an abrupt boundary. So we can solve for the field as well as the depletion layer width. And so if they are not, they are very different, then the key is that the most of the depletion region is in the lower doped region, like in this case. If you have N plus P, then most of the, because the N plus cannot deplete much. So essentially, the edge of the depletion region is essentially at the N-type boundary here. And the rest of the depletion region is in the P-type, lighter doped region. Okay. And let's see, what's okay. Again, to be optimized, it's not clear what the question means, but I suppose if it's a bipolar transistor, okay. Oh, okay. Next question is also related. So this is to be covered in chapter 9. We cover NPN. NPN is N plus P junction, emitter base junction. So in that case, well, first of all, in chapter 3, we say that the electron current, Jn, is proportional to Ni squared over Na. Hole current is proportional to Ni squared over Nd. Now for N plus P, the electron density is inversely proportional to p-type, so it's high. And but hole density is inversely proportional to n-type doping, which is very high. So Jp is low, and that's how we make a current gain in NPN, to try to utilize the difference in the in the electron current, hole current, and then we add a collector that separate the electron current. So electron current will go from emitter into base into the collector. Okay? So we will discuss in more detail in chapter 9. And for the reverse bias breakdown, we also have a chart showing that. And if it's not symmetrically doped, then most of the breakdown behavior is determined by the lighter doped, on the lighter doped side in this case. Okay, so because the field here, okay, now is dependent on the p-type doping. If p-type doping is also heavy, then the field here can be very high. Then you have a lower breakdown voltage. So that covers this question.
我可以稍微补充一下。
请。
你那个如果说你plot那个 field versus distance 或者是 junction 的那个位置，你 breakdown 的那个至少你的 body drop 是 across 那个 area ，integrate 就是 reverse bias 要跟那个 depletion region 申请，所以这是 first order， 就是说它那个一般讲起来单边的话，那个跟两边都有的话，都是 lightly dope 的话，那当然是 lightly dope peak field 比较低，然后total 那个 depletion 会比较大，所以它bias。那另外一个就是说 breakdown 最主要像刚刚老师讲，最主要就是还是 field most important is the field， 因为有 implantization 那个。所以通常要提高 breakdown voltage 就是要 use lightly dope 的junction，至少有一边是要尽量想办法有 lightly dope。所以你在 diode 或者是在 MOS 的那个 drain 会有 lightly dope drain，这以后会提到 就可以提高那个 breakdown voltage 啊，我想这大家也应该很容易了解。那至于有一个到最后一个 absolute breakdown，那个是不管在 electric 或者是什么可能的，它都有一个 maximum electric field，那个又是那个到了 extreme 的这个 case，那个它有
OK
symbol。
OK，哎，那我再补充一下，这个大部分的application actually is one-sided junction in the transistor. Either N plus P, like N-channel MOSFET or bipolar, or P plus N is in the PMOS, PMOSFET. Okay, so but usually we don't worry about the breakdown in those. Only one side is heavy because the other side is light. Okay, because when for in this diagram showing the breakdown, actually it's N plus P plus. You can see that this is P plus, Fermi level is the valence band. This is N plus, and then the breakdown voltage is low. Okay. This also indicates that we have to worry about this kind of band-to-band tunneling when the P-type doping in the NMOS is high, because N plus is already high. But if P is also high, then we have to worry about the tunneling current. Next question. Okay, I think that's the last one. How is the Shockley barrier? Okay, the barrier height indicated phi Bn is related to the metal work function minus the electron affinity, which is for silicon is fixed, and but this is for no surface states. Usually they are surface states, so this has to be empirically measured, the barrier height. But barrier height is important in the sense that you can see that it determines the phi Bn goes into the current expression, e to the minus q phi Bn. So if phi Bn is high, then current is low. If current is low, then of course the contact resistance is high. So this is contact resistivity. So phi Bn is high, then we have a problem. So from the contact point of view, we really want okay, for N plus. For N plus, we would like to have a metal that has a work function close to electron affinity. So the barrier is almost zero. For p-type, we want to have a barrier that's the electron affinity plus the band gap. Okay, so that for the p-type barrier, it's not shown here, but it goes in the negative direction. But in practice, when we make a CMOS, okay, maybe Sun Yanzhang can give some comments. But as far as I know, the same metal or same silicide is used for N plus and P plus. So in that case, we just choose mid gap. If the barrier is for mid gap, then it's the same barrier to N plus and the same barrier to P plus. Is that still the case?
Yeah, I think indeed for most of because CMOS, you have N plus and P plus, right? Contacts that you have to worry about. So typically, try to choose the mid gap, or don't make it too asymmetric. Because if you just to simplify the process steps, but then we have to use very, very heavy doping at the interface to get into the tunneling region so that we can get lower contact resistance.
Okay. So then let's cover all the questions. Okay. So we go back to where we left off in chapter 2. or okay. So you see the chart on the split CV, Andy?
Yes, please go ahead.
Yeah. All right. Let me go back to the. Okay. So in the last class we covered the CV measurement, which is very simple, two terminal, gate and substrate, right? Gate and silicon and oxide. So that's used most often because you don't have to do much. Just put on a metal dot on a piece of silicon, and then you can make contact and then measure CV. But a more sophisticated structure is after you made a MOSFET. For example, in this case, we have an N MOSFET, and so we have a source and drain. This will be covered in chapter 5. And the substrate is p-type, right? And you have gate. So in this case, the inversion layer, the inversion charge, in this case, the electron. Suppose you bias the gate such that the inversion layer is formed. Then the inversion charge is supplied by the source and drain. So in that case, it's no longer slow. Okay, it doesn't rely on the generation and combination in the substrate. Rather, it's supplied from the source and drain. So this type of CV is called a split CV. And also, when you apply the same the DC ramp plus AC voltage, but you measure current from both from the substrate and from the source. Okay, so in other words, you separate the electron and whole response. Whole response go to the substrate, and the electron response is measured by the A2 connect to the source and drain. So in that case, and then if you add them up, that's the total charge, charge. And so that's yeah. So in this case, you always get the low frequency, the so-called low frequency CV, like the case A, because even though you measure at a high frequency, but you don't rely on generation and combination for the inversion layer response. Rather, it's going in and out of the source and drain. That's very fast. So the curve is always low frequency, shown here. Now, if you divide this into two parts, so A1 and A2. A1 measures this depletion charge due to depletion of holes from the P substrate. Okay, so that's dQd over dVg. And so you can see the before immersion, okay, all the capacitance of due to the hole depletion of holes, accumulation or depletion of the majority carrier here. But once you get to immersion, then the one measured by A2, which is this dQi dVg, goes up. Before there's no immersion charge, so there's no immersion charge response. But after the strong immersion condition, and this goes up. At the same time, the depletion charge capacitance goes down to 0. That's because once the inversion charge responds through A2, then there's no need for any hole to respond through the substrate. So the capacitance goes to 0. You add them up, you still get the full CV, low frequency CV. It's just that so before that, it's the measured A1 is the same as the total, but after that, it's dominated by the capacitance measured through A2 from the source and drain. Okay? So in this way, you can get more information from this device. But you have to have a MOSFET made, which means that you have to have more lithography and more processing steps. So this is only this kind of measurement is only done after pretty much after the whole entire process is finished. Okay. The next is the effect of gate work function. Okay. So just to repeat, the condition for strong immersion, we covered, is the gate voltage equal to, there are three terms. The first term is flat band voltage. Second term is 2 psi B. The third term is Vox. And we show that Vox is related to the charge in silicon, or depletion charge divided by Cox. And the second term actually is, we are pretty sure about. It's about 0.8, 0.9 volts within 10% or so. Okay. So the most important factor is due to the first term, the flat band voltage. And so just remind, this is actually the first chart in chapter 4. The flat band voltage, okay, with negligible outside charge is the work function difference, phi m minus phi s. Okay. And so it all depend on phi m. Okay. Remember that phi s in this case is p-type. So electron affinity plus half a band gap plus another psi b. Okay. That's on we covered before. And so here I list three possible gate work function. The first one is the gate has the same work function as M plus silicon. In that case, phi m is electron affinity. In the second case is a mid-gap metal. In that case, the metal function is electron affinity plus Eg over 2 Q. The last case is all the way to the valence band. It's a P plus silicon. P plus silicon is electron affinity plus a full band gap of Eg over 2 Q. Now, so the difference is on the next chart. First of all, let's talk about so this is like the threshold voltage for strong immersion condition. So we don't want this to be too large. Okay. And we already know that 2 psi B is almost 1 volt. And there's also depletion charge. So the first term needs to be negative in order to get a threshold voltage let's say less than half a volt or so. In today's transistor, the supply voltage is 1 volt or less. So the threshold voltage needs to be something like a quarter of a volt or so. And so that calls for a negative reflect band. A negative reflect band is achieved by using an N plus silicon on the gate. It's shown here. Okay. So if phi m is electron affinity, then phi m minus phi s is minus half a band gap minus psi b, shown here. Which can, so this is minus Eg over 2 is minus 2.56. And there's other psi b, which is about maybe 0.4 or so. So this is close to minus 1. Right? So that will essentially offset the second term of 2 psi b. So the first term is minus 1, second term is almost plus 1. And then the threshold voltage is all controlled by the third term, that's the depletion charge at the threshold condition. So we'll discuss this in chapter 6. But right now I just point out that this implies that we want to use N plus silicon gate on p-type or NMOS, and vice versa, p plus silicon gate on n-type. Right? That has been the case for many generations until maybe, I don't know, Jack can point out that maybe 15 years ago.
With the high-K metal gate.
Yeah, and here's the reason. Here's one of the reasons. Okay, that's so-called polysilicon gate depletion effect. Oh, one more thing to talk about. Okay, yeah. So with N plus silicon, so even at 0, okay, this is a Venn diagram shown here. So at 0, the p-type silicon is already depleted. And that's why the threshold voltage is so low. You only have to go from here to the 2-side-B condition. Now, the reason that polysilicon gate is no longer used is because of partly because of this problem, and that's the polysilicon gate depletion effect. Okay, so far we assume that the gate is like a metal, so there's no bending in the gate. Okay, but the polysilicon gate can only be doped something like 10 to the 20. So even at that high doping, you still have some little depletion effect. Once you have a depletion effect, then the gate voltage will have additional term due to this bending psi p in the polysilicon. And also it goes capacitance, another term. Okay, before it was only 2 capacitors, C-ox and C-silicon. But now you have C-ox, C-silicon, and C-poly. Okay, so now, and so this will reduce the immersion charge density, and therefore reduce the current. Okay. So so this is a typical. This you can read the details in the book, but the CP, the depletion in the silicon, can be estimated by this parameter, and even if NP is 10 to the 20 per cubic centimeter, you still have some finite the depletion layer in the gate, okay, next to the oxide. So that when you do a CV measurement, you can see that this is for 3 silicon polysilicon doping, NP equal to 5E18, 1E19, and 5E19. Okay, so you can see that the higher you doped, the more immersion charge you can get under the strong immersion condition. But still, it's less than the oxide. So we frequently define this based on this capacitance. We go to C immersion. You can define a T immersion. Okay, so that's effective thickness as far as the immersion charge calculation is concerned. And typically, T immersion can be as much as 1 nanometer thicker than T-ox. Okay, so so when the T-ox is scaled down to below 2 nanometer or even below 1 nanometer today, we cannot pay this price of 1 nanometer thicker than the oxide. So that's why now the industry uses a metal gate instead of the polysilicon gate. Of course, the price to pay is the process complexity. Jack will talk about the processing steps in the next Monday, right?
Yeah, 9月30号 yes.
Yeah. Okay.
现在那个 the most advanced FinFET and gate around all replacement gate 全部都是用 wall function metal 来决定那个 threshold voltage。所以我想待会在那个后面讲这个 ET 啊这些的去调啊，这个在高老师的那个课程当中会提到这点。
Okay. Okay. All right. I go on. Yeah. Okay. Next topic is we call the gated diode, and so we put the MOS and PN junction together. Okay, like the one shown on the top right, and on the left is the MOS. Okay, so you have in this case it shows N plus. Well, actually this is PN junction. This is PN junction in this direction, and then we make a MOS in the perpendicular direction. Right? So it's like a MOSFET. Gate is here, and the source drain. And so in this case, we consider zero bias. PN junctions zero bias means there's no current, so it's somewhat equilibrium. In that case, everything is like what we have just covered. When you apply the gate voltage larger than the 2 psi B strong inversion condition, then you have an inversion layer formed. The 2 psi B is the surface potential. Right? It's the same as before. But if this PN junction is not zero bias, but rather reverse biased, is shown here. So in this case, we assume P-type substrate is grounded, but the N-type is reverse biased. In this case, a positive voltage, the VR. So it's reverse biased. And of course, you can see the diffusion width becomes wider. But more importantly, when we apply a gate voltage to bend the band by 2 psi B, like the middle case, 2 psi B, there's no inversion in the P-type when there's a reverse bias. That's different from the zero bias case. And the reason is that the reverse bias shifts the electron Fermi level far below the Fermi level of the P-type substrate. So in this case, there's no inversion if you just apply the gate voltage to bend bands by 2 psi B. Instead, you have to bend the band much more by 2 psi B plus reverse bias. And I'll show you later why that's the case. From this 3D plot, schematically, you can see that now the conduction band in the P-type is closer to the electron Cauchy Fermi level, which is defined by the N. Okay. The next chart. Okay, so we further discuss this. I didn't talk about this in the lecture in much detail, but it's more detail in the book. Okay, it's shown here. And so when you have a reverse bias PN junction, the electron density at P side, at minus XP, at the diffusion boundary on the P side, is given by that. With a reverse bias, the factor coming in, e to the minus QVR over KT. Okay, delta is much smaller than 1. So when we apply gate voltage that bent by the surface by 2 psi B, like in this case, which means that I multiply the first term, this term, by the e to the 2 psi B over KT, which is equal to NA over NI squared. But this equals the NA times e to the minus QVR over KT, which is much less than 1. So that's not enough to get the electron density at the surface at the minus XP to be comparable to NA. This is still much less than NA. So there's no strong inversion. But for strong inversion, we have to apply a gate voltage such that we bend the psi S by 2 psi B plus VR. Okay, so in other words, we add a factor of Q e to the QVR over KT, which will cancel this e to the minus QVR over KT factor. Is much less than 1. And then you will recover. Then we have this case when you bend it V reverse bias plus 2 psi B, and then the electron density here becomes Na, just like the inversion condition, strong inversion condition that we discussed before. Another way to look at this is now we take a look at the charge. All right, so in this case, we take a cut. In this cut direction, perpendicular to the gate. And so we don't see the p-n junction. The p-n junction is perpendicular to that cut. But when there's no bias, shown on the left, zero bias, then that's the same as before. When you there's only one Fermi level, okay, because everything is thermal equilibrium. And so when you bend it by 2 psi b, the electron Fermi level becomes such that you have electron density the same as the hole density in the bulk. But when you have a reverse bias, the electron Fermi level, and so now we have to talk about the quasi Fermi level. Okay? For the whole quasi Fermi level is here in the p-type, but for the electron quasi Fermi level, it's way down here due to reverse bias. It's now shown in this section. So now you have to bend much lower for the conduction band to be close to electron quasi Fermi level, and that will cause a strong inversion condition. Okay. At the same time, you can see that because of the reverse bias, the diffusion width is also much wider. Okay, before we have the 2 psi b in here, but with this we have to, because now the surface potential is 2 psi b plus VR, so you can so the diffusion width becomes much larger, just like shown here. Okay, much larger, and this is looking at it's the same thing, just look at a different cross section. The cross section in this direction. Okay. Last chart on this. Okay, we finish this before we take a break. You can also look at the CV curves. With assuming that you have assume that you have this situation, and we apply different. Let's see. Okay. Assume that we will apply different reverse bias, okay, and then measure the CV. So what we see is that, okay, start with zero reverse bias. Zero, okay, that's this the first started curve. Okay? And so that's just like a normal CV. This is surface potential, bias is psi s, same thing, equal to about 0.6, 2 psi b. Okay? And you have a strong inversion here. But if you apply a 2-volt reverse bias, then there's no strong inversion. Instead, the CV keeps depleting until the surface potential becomes 2.6. 0.6 plus VR is 2.6. So at 2.6, you have an inversion indicated by this increase of capacitance to the Cox value. This is anonymized to Cox. And so you can apply even 10 volts. Then you need about 10.6 for the surface potential. And so now you have a much deeper, you can see this much deeper depletion region before the inversion is reached. Okay, so all this is talk about the same thing, okay? Because of the reverse bias increase, you have to apply a higher gate voltage to reach 2 psi b plus VR, and therefore the capacitance becomes smaller and smaller. Okay, okay, time to take a break. 20 minutes. We resume at 10:10.
好 ，OK， 谢谢。那个10点10分，关掉。
我们再继续上课。
喂 ，OK，
Okay, the next topic, chapter 4, is quantum effect. Okay. If the device dimension is large and oxide thick, then quantum effect is not so important. It's weak. But now the oxide is very thin, atomic dimension, and the field is high, then the quantum effect becomes important consideration. So let's consider the how do we put what's the quantum effect on the MOS characteristics. So far, we only used Poisson equation to discuss MOS, and we used the electron density is given by the density of states without consideration of quantum effect. But if there's a quantum mechanical effect, in this particular case, it's because, for example, in this example shows the conduction band, that's the oxide, 0, that's the oxide interface. So the electron is it populates this very narrow, that's 40 angstroms, okay, so it's very narrow channel near the surface. And so if the electrons are confined in the depth direction, then its momentum uncertainty goes up, which means that the ground state is above the bottom of the well. It's not here. Rather, the ground state is here. We define as 0 here. And so basically, now we have to couple the Poisson equation to the Schrödinger equation. This is shown here, where V is given by this this potential, the conduction band near the surface. Okay? It's very strongly depth dependent, and phi is the wave function. Okay? They are coupled together because the electron density is now given by the square of the magnitude of a wave function instead of given by the 3D density of states. So we cannot use that in the Poisson equation. Instead, we use the Schrödinger equation and the magnitude of wave function to determine the electron density. On the other hand, this Vx, is the potential is the same as the psi. Okay, the Vx is the electron sees this potential. Okay, that's the same as the potential we define. So that's how the Poisson and Schrödinger equation got coupled together, and it cannot be only be solved numerically. Okay, one particular case that we can sort of solve it better. Well, we'll mention it later. Okay? But first, let's look at what's the quantum effect. The quantum effect, as shown here, on the immersion charge. Okay, on the left is the immersion charge, the classical with Poisson equation only, no Schrödinger equation. Okay? And it shows that it goes peak at the surface. That's the interface. Very shallow. That's 2 nanometers, so it's about only 1 nanometer or so. But actually, once you consider quantum effect, which of course you must because that's physics, okay? Whether you like it or not, quantum effect is there. And so the immersion charge profile actually looks like this instead of going up, because once you have the Schrödinger equation, for the Schrödinger equation, the wave function must be continuous at the boundary. So at this boundary, the wave function must go to 0 or approximately 0, except for tunneling, which we will discuss later. And and then it goes up. So the peak is somewhere below the surface. So this means that there's additional capacity. In other words, the immersion charge centroid is not as close to the surface as we think using the classical equation, but rather it's deeper. In this numerical example, it shows that this is the center of mass of the immersion layer compared with quantum with classical. So in general, quantum is deeper than classical by roughly maybe 1.2 nanometer or 12 angstroms or so, and that's in silicon. So if we translate that into the oxide thickness, that's about 3 to 4 angstrom thicker, and the effect of the quantum effect is essentially make the oxide appear thicker, or as far as the immersion charge is concerned. Okay? So this, of course, is not good news for the MOSFET performance, because that means the current is a little bit lower due to the immersion charge density not at the very surface. Now, there's one case that we can sort of solve the quantum effect better. That's in subthreshold. In subthreshold, we can actually decouple the two, because in subthreshold, the immersion charge is negligible. So when we solve the Poisson equation, we don't need to know the electron density, right? Because it's negligible. So then you can solve that, and then you put this the potential in the Poisson equation into the Schrödinger equation, and try to solve the wave function by Schrödinger equation alone. And so that's in this case. So in other words, we well, we also take an approximation that so this is the Poisson, solving the Poisson equation with only depletion charge, and there's a bending, and so there's a surface field we call it ES, okay? And so here we can see the discrete quantum energy levels. The first one is ground state, is somewhat above the minimum, okay? And then discrete from that point on. And so we can approximate for the Schrödinger equation, we can think about electron sees this triangular well. Okay, on the left is oxide barrier, which goes very high, and on the silicon side is this constant slope. Okay? So in this case, the potential function for the Schrödinger equation is like this, where ES is solved from the Poisson equation in subthreshold. So in that case, the solution for the wave function in electron wave function is Airy functions, and then we can have a analytical expression for the energy level shown here. The lowest is when J equal to 0, okay? And also the center of immersion charge. Okay? So in this particular case, it can be solved. This part is given by the depletion approximation, okay? Because we solve Poisson equation with no immersion charge, so we can apply the depletion approximation. And the other thing is that the 2 psi B condition is when we solve. Let's see, we go all the way back. The 2 psi B condition is when we say the conduction band at the surface is such that the electron density is same as the hole density in the bulk. But now there's no electron density at the surface due to quantum effect. Okay, so you bend by 2 psi B is not enough to reach threshold. We have to bend by 2 psi B plus some thing called a quantum, due to quantum effect on the inversion condition. And that's shown in this plot. So it's the shift. Shift means that you have to bend, the surface potential has to be 2 psi b plus this amount, plus this shift to reach the inversion condition. Okay. So it's a very strong function of the field, the silicon surface. The field is given by this, as I said before. And the when the field is below, let's say 10 to the 5 volt per centimeter, you see the quantum effect on inversion condition is only about, that's 50 millivolts, or about 20 millivolts. So it's not important. But once the surface, the field density, the slope becomes 1 megavolt, okay, then you can see that if it's 10 to 6 volt per centimeter, then you need to bend by more than 100 millivolts. Okay? So in other words, the quantum effect will raise the threshold voltage for this inversion condition on VG by about 100 to 200 millivolts. Okay? So this becomes a appreciable effect. Okay? So that basically that the quantum effect means that you have to consider first the capacitance is smaller, okay, because inversion charge is further away from the surface. Second, the threshold voltage is higher because we have to bend by more than 2 psi b to reach the inversion condition. Okay, so these two are the sort of quantum correction to the MOS gates. When the oxide becomes very thin, we have further quantum effect, that's tunneling through oxide. Okay, it's shown here. Okay, so this is the band diagram now, including the oxide. Oxide is about 8 or 9 eV band gap, very, very large band gap. And the barrier height is the difference between conduction band in silicon and conduction band RSL2. And that's 3.1 eV, which is high, but you can still be overcome. Okay? There are two kinds of tunneling. First one is Fowler-Nordheim tunneling. When the oxide is not very thin, in that case, you can tunnel if you apply a large bias, large voltage to the MOS, like in this case. Okay? If I have a high field in oxide, 7 megavolt per centimeter, then there will be some current due to tunneling of conduction band electrons to the oxide conduction band. This line is the oxide conduction band, and of course, then it goes to the gate. Okay? But first to the oxide conduction band because of this tip. So tunneling distance at a higher energy is shorter. Okay? So that's this. This is a very important mechanism for fresh memory function of fresh memory devices. We're discussing in chapter 12, close to the end of this course. But when oxide is very thin, by the way, for the flash, the Fowler-Nordheim tunneling, the oxide thickness is about 10 nanometer. So it's not that thin. But now the logic device, the oxide is below 2 nanometer. In that case, we have direct tunneling, which happens even at not a very high field. Even at a low field or low voltage, you can have a direct tunneling from the electron from the conduction band of silicon to the gate. Okay, this is to the conduction band of oxide, and so this becomes significant when the oxide is shallow, is thinner than about 2 nanometers. In fact, we can have a plot of the tunneling current density versus the voltage for different thickness. Compare with the off current. Now, the tunneling current, well, first of all, it's a very strong function of oxide thickness. So from 3.6 nanometer, the bottom, to 1 nanometer, the tunneling density has changed by more than 10 orders of magnitude. But this is actually it's important because we talk about the standby power dissipation or the off current, or whether it's actually it's not off, but there's no MOSFET current, but it's in standby condition. We'll go over the detail in chapter 8. But due to gate tunneling leakage, you compare with the off current, off-state current, becomes appreciable once the oxide thickness is thinner than 2 nanometers. Yeah. And okay, so that's where the high K insulator, the gate insulator comes in, which we replace the oxide. You still need a atomic layer or subatomic layer at the interface to passivate the silicon bonds, but then you have high K, which can be thick, but the capacitance, or epsilon I over Ti, can be as large as a very thin oxide. Okay. So the EOT is equivalent oxide thickness of a high K, is given by the physical thickness of an insulator, okay, multiplied by the ratio. Epsilon oxide is 3.9 times the epsilon 0, and high K can be something like 20 times epsilon 0. So this can be 1 over 5. So even though the high K's physical thickness is above 2 nanometer, but the equivalent oxide thickness becomes sub nanometer because of this effect. So this, of course, is the reason that the industry switched to high K gate insulator for the last 15 years or so. Okay, so this is the end of chapter 4. And next we go to chapter 5, MOSFET. Okay. So this is a schematic of NMOS. This is on P-type silicon, and we have the source and drain, that's N plus to N plus region. Okay, so we have a PN junction here, and between the two N plus region, we have a gate which can control the potential, okay, between the source and drain. And that's how this works. And the rest, you can see that the field oxide, that's isolation from between devices, and then you have a contact hole and the metal. Okay, and for the For the contact, there are altogether four electrodes. Okay. So the MOSFET is actually a 4-terminal device, even though we usually only use 3 terminals. 4-terminal because you have the gate, source and drain, and then substrate. Substrate usually is also called a backgate. Okay. And let's see. And so this is for NMOS. For PMOS, we have a P plus, we have an N-type background, not substrate, but the N-type background, and then P plus source and P plus drain. And then the gate try to invert the surface to P-type, okay, from N-type to P-type. But usually, in almost all textbooks, we just use NMOS to discuss the model that describe the current as a function of the voltage. Okay. Some parameters, we call it this the channel length is the distance between source and drain, and oxide thickness before. There's a junction depth xj, and there's also a w. W is called channel width. Right? So it's a 3-dimensional, but it's the 3rd dimension. Width usually is uniform in that direction, in the z direction. So MOSFET is mainly a 2-dimensional device. Okay. 2-dimensional because the gate effect is in vertical direction, but current flows is horizontal. And so it's a 2-dimensional device. It is also called it's called a unipolar because for NMOS you only worry about electron. You don't have to worry about holes because the PN junction is mainly for isolation. Doesn't play any role. In chapter 7, when we talk about SOI, you can see that you don't really need a P-type substrate. This can be undoped and still works as long as there's no conduction current before the gate is turned on. Okay, so first let me just make a historical remark. This is a milestone in MOSFET development, 1969. Before that, it's aluminum gate. Now it's polysilicon gate. And that's a major advance because with aluminum gate, you have to do the source drain first and follow this process. Do the source drain mask, and then do the source drain implant, and then you anneal. Anneal means that you heat the silicon to like 900 degrees or 1000 degrees to repair the damage due to implantation, regrow the implanted area, and then you define the gate. So the second mask is gate mask, and this mask cannot be perfectly aligned to the source drain mask, and so there'll be excessive overlap because you cannot underlap. If the gate is if on any side is not overlapping the source and drain, then that region cannot be inverted. Okay, so it has to overlap. Minimum has to be 0 overlap. So in other words, in the worst case, you can have an excessive overlap. And we will cover in chapter 8 that the overlap capacitance can degrade the CMOS switching performance by very significantly. Yeah, so this has to be minimized. And that was done by the polysilicon gate that were invented at the Bell Labs in 1969. And so now we have the polysilicon gate. Now we can apply only one mask, the gate mask. And you etch the gate, and then you do source drain implantation with the gate in place. Okay. where the gate will block the source drain ion implantation. So the source drain will be self-aligned to the gate. That will minimize the overlap capacitance. Okay, and then you can go through the source drain anneal. The reason you can do this with the polysilicon gate is because polysilicon can stand the 1000-degree annealing temperature, but if it's aluminum, you cannot anneal after anneal after implantation because aluminum melts at something like 450 centigrade. Okay, so you can. So this you have to do anneal before the gate for aluminum, but for silicon you can do it after, and that's so-called the self-aligned process. And but as I just mentioned the last hour, that the polysilicon has to be replaced when the oxide is very thin because the polysilicon has a polysilicon depletion problem. Yeah. So in the current process, it's using metal gate. As Jack mentioned, it's the so-called replacement. In other words, you still like go through here with some self-aligned process, and then you somehow cover the whole thing, and then dig out the polysilicon and refill this part with the metal, whatever metal that that you want to use for the threshold voltage control. So in that way, the alignment is similar to the polysilicon gate, but you change the work function, and also there's no depletion problem because we replace the polysilicon with metal. Okay. So even though the industry went from metal to polysilicon back to metal, but that metal is not the same. It's not the same as this metal. Okay. It's done after polysilicon, and we replace the polysilicon with the new metal. And you have to have two metals. For polysilicon, you can dope the NMOS side N plus poly, and P region with P plus. But for metal, you have to have two different metals. So there's a lot of mask and process complexity involved. But we have to do that because the polysilicon depletion problem we mentioned earlier becomes a serious performance destruction when the oxide is very thin. Okay. So still a schematic. Okay, now we define the X, Y, and Z. X is in the depth direction. 0 is at the surface on the source side. Okay. And Y is in the drain direction. The channel length is L, so source is Y equal to 0, the drain Y equal to L. And also, the reference is the source, the ground. So we usually use the ground source reference. So when we have gate voltage, it's VGS, VG with respect to source, VGS. Drain voltage, VDS, drain with respect to source, VDS. Substrate, usually we assume VBS equals 0. Okay, we discuss later what happens when VBS is not 0. But so right now we assume that the VBS is 0, so that the PN junction between the substrate and source is zero bias. This is zero bias. Right. Now we define two parameters. The psi, just like in chapter 4, it's the bending, okay, at the X and Y. Before in chapter 4 is only X because there's only MOS is only one only in the X direction. But now there's also Y direction. So the band bending can also change in the y direction. So now it becomes a two-dimensional potential. We also define another important parameter, that's Cauchy-Fermi potential, electron Cauchy-Fermi potential. Here we don't worry about whole Cauchy-Fermi level because this is a unipolar transistor, so the holes are not involved. It's mainly electron. So electron Cauchy-Fermi potential, we call it Vy. Okay? We use this notation for historical reason. So the boundary condition for Vy is such that at y equal to 0, V equal to 0. That's this p-n junction is a zero bias. It's ground. Source by definition is ground. At the drain is a reverse bias, BDS. Is a positive with respect to the source. Okay. So at L, the electron Cauchy-Fermi potential is VDS as a positive. Okay. So now we need to find a model that express the current. Let's see, the current from the source to drain as a function of gate voltage and the drain voltage. Okay. Well, we call this, by the way, MOS, of course, metal oxide semiconductor. FET, field effect transistor. Field effect because the transistor works due to the field in the oxide from between the gate and the silicon. And it's transistor because it's the 3-terminal, actually it's 4-terminal. But the current flows between source and drain. That's terminal 1, terminal 2. But that current is controlled by the third electrode. That's the gate. Okay? So source with drain current controlled by the gate. And that's the basic definition of a transistor. Okay. So for the model, we have to make many approximations. The first approximation we make is so-called gradual channel approximation. Gradual channel approximation assumes that because in principle, this potential is a function of x and y. So the Poisson equation will have two terms: the second derivative of potential with respect to x, and second derivative of potential with respect to y. And that becomes a partial differential equation, and that's very difficult to deal with. So the first approximation is that we ignore the potential curvature in the y direction because the potential change in the y direction is controlled by the channel length, L. And this chapter 5, is called long channel MOSFET. So if this L is very long, that means the potential or the voltage changes only slowly in the y direction. So in the Poisson equation, we only take the second derivative of potential with respect to x equal to charge on the right, on the other side. So that's the first, it's called the gradual channel approximation. But something is changing in the y direction, okay, because it's y, we change y from 0 to L to source to drain, something is changing. So the gradual channel approximation means that at each y, we solve a 1D Poisson equation. Yeah. So instead of solving the 2D Poisson equation, we solve 1D in vertical slices for each given y. Okay. In terms of 1D vertical slice. So current density equation we derived in chapter 2. Mobility times electron density, dV dy. This is the gradient of the Cosi-Fermi potential that determines the current. And by the way, we define the IDS to be positive because for a N MOSFET, the electron goes from electron goes from the source to drain. Okay, so the current flows from drain to the source. Current is positive charge, so from VDS to ground. But that's in the reverse y direction. So in order to avoid all this negative sign, we define the IDS to be positive. Okay, that's the drain to source current. So first, this is the current density. Current is in the y direction. Okay, because that's the only direction that the current mainly flows. And so to get current, so the current density is current per area in the x and z direction. Okay, now x and z, z is easy. That's just the width. Okay, we just because that everything is the same in the z direction, so it's multiplied by width. But for the x direction, so we have to integrate in the x direction. Okay, so we define this Qi by integrating this the volume electron density in the x direction over the immersion layer xi. Okay. So we get this Qi. Okay. Qi is immersion charge per area. Okay. This is a key parameter for MOSFET operation. Okay. Qi defined here. And so that's the immersion charge per area. What area? Gate area. Okay. So it's like MOS. And that's in the x direction. Okay. So once you have the gate area, and then the gate width is W. Right? So Qi times width, okay, becomes the charge, and then you have a dV dy. And here the mobility becomes mu effective because in principle the mobility may change. It may be a function of depth. Okay, so but effectively we can dump it into a parameter we call it mu effective. And we'll discuss a little bit later. So based on this equation, so once we define this charge per immersion charge per area, then we can multiply the dy over and then integrate on both sides. This charge is a function y, but we can also consider the immersion charge that's a function of v, because it's shown here v is a function of y. Okay, so vice versa, y is a function of v. So v and y can be interchanged. Okay, so Qi is a function of y. It's also a function of v. Okay, because of this relationship. So we change Qi to Qi v. Then we can integrate, multiply dy over and integrate on both sides. The left side is easy because IDS has to be continuous. The source drain current cannot be y dependent. Whatever the current that's going out of the source has to be the same as the current flowing into the drain. So IDS is a constant. Okay. The integrating of with respect to y becomes simply L. L is the L is the distance in the y direction. Okay? Right. So we integrate that constant, which becomes I becomes, the IDS become constant, I times L. And then you can divide L back to the right side. Right? So you derive this expression. The current is mu W over L. The L is divided from the left side. Integration of Qi with respect to dV. As I said, we define IDS to be positive, but Qi is negative because this is NMOS. So Qi is negative charge due to electrons, mobile charge are electrons. So minus Qi is positive. And you integrate from 0 to L, or from V equal to 0 to VDS. Okay? So once, if you know this function, then you just integrate, and then we get a current. Okay? So that's a simple result of the gradual channel approximation. Okay. So just a reminder that we solved this from chapter 4, which of course is 1D, but according to the gradual channel approximation, we ignore the second derivative of potential in the y direction. So, so this equation is still valid under gradual channel approximation. So all that discussed in chapter 4 can be applied. Okay. So the key result that we want is here. The electron density at any point x and y is given by Ni squared over Na e to the q psi minus v over kt. It's basically this expression in chapter 2. Okay. EF minus EI. Okay. Now EF becomes minus QV. Okay, because this is the Corsi-Fermi potential. There's a negative sign, and EI minus EI becomes psi. Psi is the band bending. Okay, so from this we can write in this way, okay, which is the same as in chapter 4. Right? N equal to Ni squared over Na e to the q psi over kt. In this case, v equal to 0, so there's no v. But and the psi is the band bending, right, which is defined the same way. In this case, we define psi to be the band bending with respect to the p-type substrate. Okay. And also, in chapter 4, we have the electric field. Okay. You recall that by one integration of the Poisson equation, this Poisson equation you can integrate once, right? But not twice. Integrate once, you get the electric field or d psi dx. That's shown here, okay? And that's equal to this. So that the right side is the integration of that, of the charge density. But then, of course, you cannot integrate because you have to take a square root and becomes a very complicated expression. But we can still use this, with the exception that there's an e to the minus qv over kt inserted. Okay, before, in chapter 4, v is 0. Right? When we are integrating this, there's no v because v is 0. But now we introduce a v. V is a function of y, okay, and it's such that the electron density is reduced by this vector, okay, and that's because if you look at it here, it's n equal to the EF. EF is minus QV, okay. So the higher the voltage, the lower the electron density. In other words, if you look at this again, for a given gate voltage, the electron density will decrease from source to drain because V goes up. V is the quasi-Fermi potential for electron. So for higher quasi-Fermi potential, for the same gate voltage, electron density will decrease according to this, right? And not putting that factor here. And as we mentioned, that the condition for the surface inversion when it's 2 psi B plus the reverse bias of p-n junction. Now let's go back to the MOSFET picture. Okay? So the p-n junction between substrate and source is 0. Assuming that the substrate is 0, this is 0 biased, but on the drain side it's reverse biased. Okay, so this is like the non-equilibrium MOS that we discussed earlier today. And so when the reverse bias is essentially a function of y, okay, because v is a function of y. Okay, so v can be considered as the reverse bias of the p-n junction at y, okay, which is 0 at the source and the VDS at the drain. So the condition for surface inversion is 2 psi B plus Vy. Yeah. And the maximum depletion layer width at the inversion, okay, we put this in as the psi s. The psi s has to, this is psi s, x equals 0 at the surface as a function of y. And so we put that in the psi s. And so it goes up from source to drain because Vy goes from 0 to VDS. That's what we showed here. Okay, sort of schematically. And the depletion region sort of increase because the closer to move to the drain. Also, you can see the reverse bias p-n junction has a wider depletion width. So is the MOS depletion width. Becomes a little bit deeper because of the Vy factor. I finish this chart. So n the electron density as a function as the point x y is given by that, but we know y and v are interchangeable, and psi is a function of x and y. Okay, so n as a function of x y can be considered as n as a function of psi and v, and because that's much easier. So that expression becomes like that. So when we integrate the qi, remember that we integrate qi to get qi integration of this volume density in the depth direction. Okay, so we change variable. It was n integration n dx becomes n d psi and divided by d psi dx, which is the electric field. So this qi becomes this integration with respect to the potential, but this is still a function of v. And then we put in the this expression. Okay, so qi is the integration with respect to psi, and then you integrate it again with dv, so become a double integral. And that double integral is called so-called the Poisson double integral. Okay, and so the whole thing looks like this. This is qi. This whole thing goes into here, except that you take the q out. And so this is the first step of the MOSFET current model is to apply gradual channel approximation and to derive the pulsar double integral. So we take a 10-minute break and we'll resume at the 11:10. Okay.
Okay.
哦，你要问老师考试的问题。
有什么问题吗？
因为我们就是第一次考试要在什么时候呢？
我是第6周嘛，对吧？我看一下，
October 7th, right?
10月7号，
Okay, okay.
7号，就是2个星期，对吧？2个星期。
对。
我会叫贴 make announcement。
那老师，请问有公布考试范围吗？
我会 make announcement before
Okay.
before next week.
Okay, okay.
Okay. It's 2 weeks from now, and I think we'll basically cover 3 chapters, but to be announced. And it'll be 1 hour in the third hour of the class, 2 weeks from now. Okay?
Okay.
Anyway, details will be in the announcement. Okay. So we continue. So we talk about this pulsar double integral, okay, which is still very tedious to do even numerically, okay, because integrals takes a lot of computing time. And by the way, there's one more thing that's important. This integral, okay, this integral is Qi, right? Qi, I change the integration change from x to psi. Okay, psi at the surface of course is psi s. Okay, and the lower limit is psi b, which is the basically the intrinsic limit. So it's from psi b to psi s. Okay, and so furthermore, the psi s. So we have to solve psi s. The psi s is this one that we have from chapter 4. Okay, see, remember we have a gate voltage equation that VGS equal to V flat band plus psi s plus QS over Cox. QS is this because is from Gauss law. Q is given by the electric field, the ES at the surface. So you change the other side to psi s, okay, and that gives, and with the square root psi, that gives the that's here. And we only keep 2 terms because only this term and this term, these are 2 important terms. All the rest are dropped because it's negligible. So Q psi kt and Q psi minus v, okay, and then square root. Okay, so this becomes a main equation for MOSFET modeling. Basically, this equation for a given VGS is a relation between psi s and v, but it's an implicit equation. Okay, so for given gate voltage, psi s is a function of v. In other words, the psi s change from source to drain, as we did before. The the psi s is 2 psi b plus Vy, and the V is changing from source to drain. So psi s is a function of V based on this. But it's implicit, okay, because psi s appears three places, here, here, and here. But V only appears once. So this equation can be solved for V explicitly. Data will make use of that later. Okay, so this is the so-called post double integral. And now to simplify it further, okay, because the double integral is too tedious numerically, and so now we introduce the so-called charge sheet model, okay, which is the next approximation beyond the gradual channel approximation. In this model, we assume that the inversion charge is very thin at the surface, so like a sheet of charge, and there's no potential drop because it's so thin. Okay, you can, if you integrate a charge with respect to x, you get a field, okay, from Poisson equation. But the field is and you integrate the field again, you get a potential drop. But if the layer is very thin, then you integrate and you get essentially negligible potential drop, and that's the so-called charge sheet model. Or we can think about the depletion charge. Okay, this is from depletion approximation. Okay, that this is QNA WD, where WD is given by this with size of the surface potential. Okay, but now we assume that this expression is valid even in inversion. That's the key of the charge sheet model. Okay. Before, we know this is valid for psi s less than 2 psi b. But this model says that QD is given by this even if psi s is beyond 2 psi b. In fact, in chapter 4, we noticed that QD after strong inversion doesn't really change. Okay, but that's just fine because psi s beyond 2 psi b doesn't change much either. Okay, so this is a good approximation in that respect. Okay. Now, if we know depletion charge, then we can find out the inversion charge because we know the total charge. Total charge is given by this expression. Right? Remember the gate voltage equation? This is QS. So QS is this square root times this square root. Okay, and that's the total charge. Minus QD is the inversion charge because, come back to here, this is the total charge. Okay, but there's a square root. So you cannot separate out depletion charge and inversion charge when the inversion charge is large. When the inversion charge is small, you can do that. Okay, that's a subthreshold condition. We'll do that later. But in general, in strong inversion, you cannot separate out depletion charge and inversion charge. So we said the inversion charge is this total charge minus the depletion charge in this model. So total charge, but we know the total charge because total charge is given by VGS minus VFAB minus psi s times Cox. Okay, because that's the total charge, and as a function of gate voltage, right, you can move everything to the left side, the first two terms to the left side, and multiplied by Cox, and that's the total charge. Okay, so the inversion charge now becomes the total charge, this term, minus the depletion charge, which according to the charge sheet model, we apply the depletion approximation even into strong inversion. It's shown here. Okay. So So this allows Qi to be expressed as a function of psi s. For a given gate voltage, there's only psi s. Okay. So now we can integrate the, remember that the IDS is integration of Qi with respect to dV. Okay. We don't know that Qi is a function of V, but we know Qi is a function of psi s. So we change the variable. This Qi dV becomes Qi dV d psi s d psi s. Okay. And so this term is given by this expression. Qi is a function of psi s. This one, okay, is obtained from differentiation of this this expression. This expression is by looking at this one, and then you solve V. Okay, so you move everything to the left, move this to the left, and divide by that, and then square, and then divide by that, and take a log. Okay, because in this implicit equation, V only appear here, so V can be expressed in terms of psi s in the explicit expression, and that's what we have here. Okay, so from that equation, we can solve V. Okay, notice that as I use, we have a square root, so this is squared, and then minus, and then you take a log, and it all follows. So now we can take a derivative of V with respect to psi s, because V is a function of psi s. Is this. So dV d psi s is simply due to this expression. So this gives you dV ds, dV d psi s, and Qi is given by that. So now we have the current. So the current is let's see. So the current is this one, this Qs times dV d psi s, which is that. This has 1 plus something. So 1 is that, and then Q, yeah. So Qi okay. So the one is Qi, and the second one is a fraction shown here, like this, and then function of psi s. Okay, so now you can see that there's only psi s. Okay, so in principle, the double integral becomes a single integral, okay. And which is much easier to execute. Okay. Furthermore, we can make another approximation so that this integral can be done analytically. Okay, and that is this aspect, because we notice that there are 3 terms. The third term is a kT over Q, which is small. Okay, only 26 millivolts. So so the third term is not important unless the first and second term happen to cancel each other. So if so we substitute this expression, first term equals second term, into the third term only, and we still keep the first and second. But we put this in here, that makes it much easier to integrate, because the denominator now becomes the square root of psi s. Okay, so integration can be carried out analytically like this, and you have all this the psi s square, psi s to the 3 halves from here, and all that. And the integration limit is psi ss to psi sd. Psi ss is the surface potential at the source. Psi sd is the surface potential at the drain. But to evaluate the psi S and psi SS and psi SD, we still have implicit equation to solve. Basically, it's given by this equation. Okay. For a given gate voltage at the source, V equal to 0. So you solve this equation for psi S with V equal to 0, and that's psi SS. Psi S at the source. And then you solve this equation again, but V with V equal to VDS. And that solution we call the psi SD. Okay. Because this equation for a given gate voltage is implicit equation for psi S. Okay, so this is still involves the solution of implicit solution to this equation with V equal to 0 and V equal to VDS. And now we solve psi SS and psi SD. And then everything is analytical. Okay, so this is the end of the charge sheet model. It's still not explicit because we have to solve implicit equations. But this model is valid for all regions of MOSFET operation. Okay? There's no assumption that it's below threshold or above threshold, or in the linear region or in the parabolic region. So this is still a so-called continuous model. Okay. Now to further the next step, to get explicit expression, then we have to make regional approximations. Oh, first of all, okay, and that comes later. First, let's look at the saturation behavior. This is the base. This is numerical solution to this equation. This equation. Okay. So for a given VGS, this equation can solve psi S as a function of V. And that's part of you. Excuse me. We assume 3 gate voltages. 1, 2, 3. 3 curves. And psi S is vertical. V is x-axis. For VGS equal to 1 volt, it's below 2 psi B. You can see that. Even V equal to 0, okay, it's about 0.6 or something. 2 psi B is here. It's below 2 psi B, so it's so it's subthreshold. In subthreshold, you can see that the psi S has no V dependence, and that's can be understood because only V dependence comes from this guy. This is an inversion charge. If it's a subthreshold, this term is negligible. So the effect of V on psi S is like nothing. Okay. So this gives you a psi S with this term negligible as a function. So it's constant function of V. Shown here. That's the lowest curve. Then we increase VG to 2 volt. Okay, now psi SS is here. It's almost 1. It's 0.9 something. Now it's beyond 2 psi B. So now it has a V dependence. And the V dependence, based on the 2 psi B approximation, is the dashed line. This dashed line is psi S equal to 2 psi B plus V. So it's the slope is given by this V, right? and 2 psi b is the intercept. That's shown here. All right, so this curve, okay, this dashed approximation is a good approximation. In the initial value, you can see that psi s is a little bit beyond 2 psi b, but more or less follow the same slope until this point. Once you get here, the psi s doesn't go up with v anymore. Okay, v is still going up, but psi s become constant. And that's because that you can see from this expression. So as I said, for a given VGS, when v goes up, psi s goes up. Right? And that gives you the v. But at a certain psi s, this square bracket becomes 0. So log 0 is minus infinity, which means that v equal to infinity. Okay, so there's a maximum psi s for that given VGS, solved by the square bracket equal to 0. And that's this value here. Okay, so for a given VGS, there's maximum psi s, beyond which psi s doesn't go up anymore. Okay. If you go even higher VGS, okay, 2 psi b is still approximately the same. Now you follow this line. Now you can go to a higher maximum psi s before we go to infinity. This means the current will saturate because because current is given by that between psi s and psi st. Now psi ss is both are function of VGS, but only psi st is a function of VDS. When you change the drain voltage, psi ss doesn't change. That's at the source. Only psi st changes. That's V equal to VDS. Right. But if psi st has a maximum, that means the current doesn't go up anymore. So you can see that for whatever value of VGS, psi ss is given by the value here at v equal to 0. Psi st is given by the value of psi s at whatever v. Okay. But psi st has a maximum as a function of VGS. Okay. Once you psi st reach this plateau, then you can increase VDS, but there's no current increase. So this means IDS saturates at the VDS at some VDS saturation. In this case, VDS is about 0.5. Here, VDS is about 1.3. Okay, so the current goes up because psi st keeps going up until about maybe 1.4, and then it doesn't go up anymore. So the current saturates at the VD sat about 1.4 here, and about 0.5 here. Okay. So we already can see that this charge sheet model implies that the MOSFET will have a saturation behavior as a function of VDS for a given VGS, and that saturation value can only be increased if you raise the VGS. Okay. So much for the discussion of this charge sheet model to this point. Now, after that, we have to have a so-called regional current model. Okay. That's to obtain explicit expression of IDS as a function of VGS and VDS, gate voltage and drain voltage. And that approximation is psi S is equal to 2 psi B and psi S D equal to 2 psi B plus VDS, which is exactly this dashed line. Okay, this dashed line is psi S equal to 2 psi B plus VDS. But we know that this dashed line is only valid beyond inversion. It's not valid when VGS 1 volt. Okay. It's only valid when VGS beyond the threshold, and also for VDS before saturation. Okay. So only for this range. So now, and then we can express the IDS in this form, the current. Okay, this current with the psi S is equal to 2 psi B and psi S D equal to psi B plus VDS. Okay. And then we obtain okay, so now it's explicit. But keep in mind that this is no longer valid for all the range of MOSFET bias. This MOSFET has to be biased above threshold, but below saturation. Okay, then we can apply this. So this explicit model, current model, is only valid under these conditions. Yeah. Okay. So this is so-called a piecewise model or regional current model. Okay. Because it's only valid in this region. Once you go beyond, like in subthreshold, we need a different model. We'll discuss that later. In saturation, we also need a different model. So this is only between above threshold and below saturation. And this is still a little bit complicated because of VDS to the 3 halves. So we can expand this into a power series. Okay, the zero order term, first order, second order. Okay. Zero order cancel with 2 psi B. So we have this term and this term. Okay. And so this one is linear in VDS that can be combined with the linear VDS in the first term. Okay. And then this one is VDS square, the second order term, that can be combined with this VDS. Okay, so we'll discuss that next. Okay, so first we consider linear region. Linear region means small VDS. Okay, so that we only consider the first order of VDS. In other words, this whole thing becomes only that one. The third term is dropped. The first term is cancelled. Okay, so it's only this 3 halves. And for that, we can express in the linear region IDS equal to this. So IDS is proportional to IDS, VDS, like a resistor, and but with this VGS dependence expression here. And this can be written, okay, as VGS minus VT. Well, VT is called the MOSFET threshold voltage. Okay. That has 3 terms, like we discussed in chapter 4. The first term, infrared band. Second is 2 psi B, surface potential. And third term is the charge, diffusion charge divided by Cox. Okay. And So this corresponds to the simple IDS equal WQIV. V is the velocity. Okay, in this case, the velocity is mu times the field. Field is VDS over L. Okay, VDS is the potential from source to drain, voltage between source and drain, divided by L is the field. Field times mu is V. And the rest is QI. QI is W is here, so QI is C ox Vg minus Vt. This can be understood very simply. Okay, and if you plot that, you plot this is the dotted line. Okay, so the IDS is function of VGS. Okay, so IDS is 0 until VGS equal is beyond VT. Then it goes up linearly with a VGS. This is for a given VDS, given some low VDS. Of course, we know that it's only valid above VT. So below VT, this becomes negative, and this model doesn't apply anymore. Another thing is that compared with the charge sheet model, which is solid line, without the piecewise approximation. Again, piecewise approximation is this approximation or this approximation. If you don't make that approximation, then you actually get this one. So the actual current is lower than the piecewise model. And the reason we can say that is due to inversion layer capacitance. Because this one, according to this one, QI is C ox Vt minus Vt. So this is C ox. C ox means that the inversion, the silicon capacitance is infinite. That's why the C ox and the C silicon in series is given by C ox. But in practice, C silicon is large, but not infinite. So it's due to inversion layer capacitance and the solid curve. And eventually they will approach C ox, okay? Because C silicon goes up with VGS. So that's the linear region. And inversion layer capacitance. Okay, that's what I sort of explained. That go back to the capacitance model. You have CD and CI and C ox here. Okay. If you assume CI is infinite, then the C inversion is simply Vg minus Vt times C ox, only C ox. But in reality, there's also a CI, then it can be expressed in this way, okay? Which is almost C ox, but a little bit less than C ox. That's what is shown by the slope. It's a little bit less than C ox, especially when you are close, when you are at a low gate voltage close to VT. And then we have the saturation region, IV characteristics. Saturation region VDS is large. So here it's first order. So now we keep this term as well. Okay, again, zero order cancel. First order term give you, combine with this, give you VDS. And then second order term is VDS square, combine with that VDS square, give you this. So that's the linear model, VGS minus VT over VDS. But the second order, the quadratic VDS square term given by that, with effect of M. This M, mathematically, is given by 1 plus this factor. Okay. This all follows from here. 3/8 not. By the way, this 3 is cancelled because there's a 3 here. So M is 1 plus or that. This is CDM. CDM is the maximum diffusion capacitance. In other words, if you put the psi s equal to 2 psi b in the diffusion capacitance, MOS diffusion capacitance, you get that. Okay. So CDM is epsilon silicon divided by WDM. Cox is epsilon oxide divided by Tox. Okay, so this can be expressed as 3 Tox. 3 is epsilon silicon over C epsilon oxide. Silicon is 11.7 dilute constant. Oxide SiO2 is 3.9. Okay, 11.7 divided by 3.9 is 3, or almost exactly 3. So the 3 Tox over WDM. This M factor is very important in the MOSFET model. It's called the body effect coefficient. We'll look at the physical meaning of that later, and then in the next chart. But first of all, this equation is plotted here. Okay. First of all, this entire model is only valid before saturation. Okay. So to the left of this dashed line. This dashed line is the saturation. Okay. So the low drain is linear, the first term, and then the second term, the second order term is negative, which means that it bends over. This is actually parabolic, with the apex given by the saturation current. And so this parabolic curve, the apex can be solved. That's the maximum current, what we call the ID saturation. Okay, ID saturation, and that's given by VDS equal to VG minus VT over M, mathematically. Now, so the first term is VG minus VT squared over M. The second term is VGS minus VT squared over 2. So you have so this is the second term is half of the first term. So you have a half of first term left. That's where this factor of 2 comes from. So this becomes the familiar expression for the MOSFET saturation current. It's a function of VGS, okay, which happens when VDS is beyond the VD set, which this piecewise model doesn't work anymore. I mean, if you follow this actually goes down, okay, because this is parabolic. Okay? So beyond the maximum, it goes down, okay, for every case. But of course, we don't follow this model because it's not valid beyond that. Instead, we draw a line because we understand from here that once you reach the saturation, the current doesn't go up with VDS anymore. Okay. So this part is not from the piecewise model, but it is from the charge sheet model. Okay. That's valid even beyond saturation. Okay. So now let's look at what does this M mean? First of all, M is always larger than 1. It's 1 plus something. Okay. Next is that you don't want M to be large because large M means that the current is smaller. Also, it's saturated at a larger VDS. Okay. But it has to be larger than 1. So typically maybe 1.2. So it's larger than 1, but not too much greater than 1. Maybe 1.3 maximum. Okay. And that's the typical case. So what is M? Okay. Physically, there's a simple expression. a simple explanation of M. We can consider the VGS. We apply VGS between the gate and the silicon and the substrate or the source. Source and substrate are bounded. And so there are two capacitors, COX and then CDM. CDM is in silicon, COX is in the oxide. And psi S is the surface potential, is the potential here. Okay. Now, if we want to show graphically, because there's a factor of 3 between the two dielectric constant. Okay. So we make this 3 TOX. 3 accounts for the dielectric constant ratio. Okay. So now we can have a straight line instead of a line of changing slope. Okay. And so we can consider that when we change VGS by a small amount, delta VGS. Okay. So here is at a certain VGS, and then we change VGS. So this point moves, but this point doesn't change. The substrate is grounded. Okay, so that's the pivot. Okay, so the line will change like that. So for the surface potential, it changes by delta psi S. In other words, for a given change of gate voltage, okay, the change of surface potential is somewhat less than VGS. Okay, and so we can express the ratio between VGS, delta VGS and delta psi S is the ratio of WDM plus 3 TOX divided by WDM. Okay, and that's M. But M is defined as delta VGS over delta psi S. Okay, and that's WDM plus 3 TOX divided by WDM, or 1 plus 3 TOX over WDM. That's exactly what we have here, 1 plus 3 TOX over WDM. So the physical meaning of M is that we try to control the immersion charge in silicon, okay, by controlling the surface potential. But we cannot control the internal surface potential. We can only control the external gate voltage. But there's a difference between the external gate voltage and the internal surface potential. And that is given by M. Okay. In the ideal case, M equal to 1, which means that for whatever gate voltage change, you have the same surface potential change. That's when this point is infinite away, when WDM is very far away. Okay, so from the M point of view, you want WDM to be large. But in chapter 6, but this is for long channel device. In chapter 6, we'll talk about short channel device. It turns out that WDM cannot be too large. Okay, so for short channel, you have to choose somewhat optimized M. Okay, and so in any case, the physical meaning of M is the ability for the gate to control the surface potential. Okay. And that is given by this definition, delta VGS over delta psi S. Or you can say the delta psi S over delta VGS is 1 over M. Okay. It's the efficiency of the gate voltage to control the surface potential. You will see M in MOSFET models and many places. But let's look at the immersion charge density. From immersion charge density point of view, from as a function of V, the Qi is a function of V. in the charge, okay, in the beginning of charge sheet model, let's go back. Okay. We have QI equal to that, right? And when the Y changes from source to drain, right, psi S will change. Well, first of all, we can make an approximation. By expanding, yeah. Where am I? Oh. Psi, okay, you let psi S equal to 2 psi B plus V, and you expand this square root into zero order and first order, okay? And then you get this expression, which is the same as Cx Vg minus Vd minus Mv. Okay? So inversion charge density can be expressed as a function of V. And so at the source V equal to 0, you have a maximum immersion charge. At drain V equal to VDS, you have a lower immersion charge. Right? So if you plot this QI, this Cox Vg minus Vd minus Mv, this dotted line here. Okay. But current is the integration of this function with respect to V. So you integrate the area under this straight line, this triangular area, and that's the current. Okay. Saturation occurs when Qi equal to 0. Qi equal to 0 is when V equal to VGS minus VD over M. Right? That's this point called VD set. So at the VD set, the area under this Qi curve becomes maximum. If you go beyond, it's going to decrease because the area becomes negative. Right? So let's see. Yeah. So if you follow the charge, the regional model, the piecewise model, it will go down. But according to charge sheet model, is supposed to be constant. Okay. But actually, we have an even deeper problem because this says that at the saturation point, Qi goes to 0. Okay. But from current continuity, Qi times V is constant because the current has to flow. So if Qi equal to 0, that means the V has to be infinity, which means the field has to be infinity. Okay. So once you are at the saturation point, actually the gradual channel approximation will break down. Okay. So we go back all the way back to gradual channel approximation. Okay. Assuming the vertical field is stronger than the lateral field. But once you are at saturation, the lateral field has to be very large to sustain the current continuity because the inversion charge density is very low, approaching 0. So once you are above saturation, gradual channel approximation is no longer valid. Okay. This is called GCA. Okay. So for saturation, you will need a so-called non-GCA model. Okay. That we'll describe later. Okay, so this is the end of today's class, and We'll continue next week. Okay.
OK。Professor Tao, there is no questions.
Okay.
好，谢谢陶老师。
Okay. See you next week.